Okay, good morning. How was your long weekend? Okay, this kind of long weekend is great, but it kind of throws me off too. I kept thinking today was a Monday. All right, so we are on lecture 6. And in the last class, we were talking about pressure distribution, and we concluded the class by pointing out how the area inside the CP curve between the upper and lower surface, if you plot it as a function of x over c, that area is essentially the lift coefficient, very, very close to the lift coefficient. So the other thing we can do now is think about how this area is distributed between front and back, right? So, okay, so the area is lift coefficient, but then does it matter whether it's loaded up here or loaded up here? And that's going to tell us about pitching moment. So let's talk about the pitching moment coefficient. And for now at least, let's just look at pitching moment about the leading edge. Like I said, when you talk about moment, you have to talk about what point that moment is defined. And when we talk about airfoils, we'll usually say pitching moment per unit span. So positive direction for M is as shown above. So when you look at the CP distribution, let's say something like this. So we talked about how the loading at any chordwise location on the airfoil, so let's say at this portion of the airfoil, if we say the vertical load is delta y for just that little piece of the airfoil, then that's essentially equal to the area between the CP upper and lower curves, but only for that area, right? So for that region. And so what is the contribution to moment about leading edge due to this portion? So let's say this is at some distance x. So if we call this delta MLE, delta meaning the portion of moment just due to this segment of the airfoil, what is delta MLE? Go ahead. What about the sign? Minus, right? So it will be delta y times x. And so if you integrate all of that due to all portions of the airfoil, the leading moment about the leading edge due to the entire pressure distribution is from x equals 0 to 1, or x equals x over c equals 0 to 1, delta y times x, well, times x x over c. Or we can write this as x equals 0 to chord delta y times x. Okay, so so to put this as coefficient form, we know that pitching moment coefficient is moment over half rho v infinity squared c squared dz, and we usually take dz's for, if you take 1 unit span, dz is 1, and so that becomes okay. So it turns out that usually we are more interested in pitching moment about the quarter chord rather than the leading edge. We'll actually go into details of why this is so very soon, but for now let's just press on. So that means we are more interested in this moment. And so the moment arm is now smaller, right? Because this moment arm is no longer x, but it is x minus c over 4. So this expression now becomes is or if we assume then if chord is equal to 1, okay, so what we're trying to do is connect all this with the CP distribution. So let's just do a quick sort of thought exercise. Okay, so I'm going to draw two CP distributions. So let's say we have one CP distribution that looks like this. And then I'll draw another CP distribution in a different color. Okay, so these, let's call this red airfoil CP distribution, and this is the blue airfoil. First of all, what can you say about the lift coefficient of these two conditions, these two airfoils? Let's say the area is the same between the curves. Yeah, so lift coefficient is the same, right? So because the area is the same. Now let's talk about pitching moment coefficient, and pitching moment of interest is about the quarter chord. So we'll talk about CMC over 4. What can you say about these two airfoils and their pitching moment coefficients about the quarter chord? Which one will have more or less or more moment? Okay, so first let's think about the sign of the pitching moment about the quarter chord. What do you think will be the sign for these two? This is the positive sign, right? This is, by definition, this is the positive sign convention. What's going to be the sign?
Blue one will have a positive.
Okay.
Red might have a negative.
Okay, so it seems like the red, clearly the red is going to have a negative pitching moment coefficient because you have a lot of lift acting, upward lift acting behind the quarter chord, so that it will cause a moment like this, which will be negative. The blue is, I mean, this is just a sketch, so it's hard to say. But what it seems like is the blue has more lift in front of the quarter chord and less lift here. But then also keep in mind that even though it's less lift, this has got much more moment arm. So this, even though this is a small amount of lift, it's got a big moment arm compared to this. So, I mean, you can't say it's going to be negative or positive or 0, something like that. But clearly, the red airfoil has got more negative CM about the quarter chord than the blue. So, So that's the power of CP distribution. So just by looking at the CP distribution, you can say something about the lift coefficient and pitching moment coefficient about the quarter chord. And it starts to get useful for airfoil design too. Later on, we'll see that if you say an airfoil has got too much negative pitching moment, then you know what to do. You have to distribute the CP more towards the front. And that's the sort of insight it gives. We haven't even talked about drag, because drag is a viscous effect, but it turns out CP distribution has effect on drag as well, because it controls boundary layer. And we'll see later that it also controls the stall, because CP distributions control boundary layer, and when the boundary layer starts separating is when stall occurs. So we are going to keep looking at CP distributions quite a bit as we move forward. Okay, so what we are going to do now is talk about some couple of new terms. Again, for many of you, you're familiar with this, but maybe it's always good to review something. And for those of you who don't have an aerospace background, this is always good to discuss. So we're going to talk about two new terms: center of pressure and aerodynamic center. And people sometimes start using these things interchangeably. They are not the same. They are very distinct and different. They've got very different meanings. So let's talk about aerodynamic center and sort of write the definition for it. Okay, so by definition, the aerodynamic center is that location about which pitching moment coefficient does not change with lift coefficient. And for pre-stall conditions, for most airfoils, CL and alpha have a linear relationship. So we can also say that it's that location about which Cm does not change with alpha. For most practical purposes, these two are the same until you go to stall and beyond and stuff like that. So we will see later when discussing thin airfoil theory, which I'm going to write in short form as TAT, that the aerodynamic center, which we shorten often and write as AC. So the AC for an airfoil in subsonic flow is at quarter chord. So this is why pitching moment about the quarter chord is often more relevant than pitching moment about leading edge or trailing edge or something else. So for an airfoil in subsonic flow, the aerodynamic center is very close to the quarter chord. It might change. For some airfoils, it will be slightly forward, maybe 24%, some it might be 26%, but in general, we can say it's at the quarter chord. And from theory, from thin airfoil theory, it's exactly at the quarter chord, but thin airfoil theory is got some approximations because of which it's not a perfect match with reality, but it's very close, especially if you're looking at unstalled condition and like cruise flight and climb flight and so on. So this aerodynamic center actually connects to, this is for an airfoil, right? There is also an aerodynamic center for the wing, and there's actually an aerodynamic center for the airplane. What is the airplane aerodynamic center usually called? Neutral point. Neutral point is the location on the airplane front and back axis at which if you put the center of gravity and go flying, the airplane will be neutrally stable. Neutrally stable is borderline between stable and unstable, right? So that's why it's called neutral point. It's just essentially it's the aerodynamic center for the whole airplane, but because that corresponds to neutral stability, people started calling it neutral point. Neutral point or NP. Okay, so this is what aerodynamic center is. Now we said there are two terms. The other is the center of pressure. So let's see what that is. Which is denoted by Cp, usually capital C, capital P. So just don't confuse it with coefficient of pressure with this, which is capital C and subscript small p, right? So there are two Cp's. One is coefficient of pressure, another is center of pressure. So let's draw some Cp distribution. As always, we are drawing the Cp with negative going up. Some Cp distribution. And let's think about the airfoil below. Okay. What is the center of pressure for some pressure distribution like this? Where do you think the center of pressure will be for this pressure distribution? Will it be at the leading edge, trailing edge, somewhere in between? Yeah, so it's the centroid. It's the centroid of this distribution, right? So I'm going to say maybe it's here, just in the sketch. And this location is XCP. So essentially it's, if you take a little piece of the airfoil here, you will have some small delta y. Like that, if you take another piece here, you'll have another delta y. The center of pressure is at that location where this entire resultant force can be assumed to act. With no accompanying pitching moment. So in a sketch we can say that you can take all of this area, and if you concentrate it as a single force, where should you put that force to get the same static equivalence? So let's put that in words and define it better. So it's kind of like center of gravity, right? If you have a mass distribution, where do you put the total weight for this distributed mass? But the key to that is there should be no accompanying pitching moment. So for example, if you want to lift an object, you can lift it from anywhere, right? I can lift this from the back, but if I do that and want to keep this level, I'll have to apply a moment, otherwise it'll just fall off. And like that, if I want to lift it from this end, I have to apply a moment, otherwise this will fall off. But there is a point along this object where I can lift it without having a moment, like I can tie a string and lift it up and it will stay level. So you're not applying a moment. So center of pressure is like that. Where do you put the resultant force with no accompanying moment? And for studying CP distributions, or for studying for knowing the center of pressure, it is most useful to look at so we know that airfoil loads come from both pressure and shear stress. So we saw this earlier. The pressure distribution is going to maybe look something like this. And the shear stress distribution is going to look something like this. So even though both of these contribute to the forces, for the two particular things we are studying right now, lift and pitching moment, these shear stresses don't contribute much, right? This force is mostly in the chordwise direction, and it doesn't have any moment, right? The moment about this point is comparatively small because the y distance is small. So shear stresses do not contribute. So for all practical purposes, when you're looking at lift and pitching moment, it's primarily driven by the CP distribution. So let's draw the CP distribution and some equivalent total forces. So let's say you have an airfoil and you have some pressure distribution that maybe looks like this. I should have drawn this arrow down. Something like this. Now this whole pressure distribution we saw causes or has a resultant force R, and that R is essentially equal to lift in inviscid flow, because there is no drag, right? Lift and drag together contribute to R, but if there is no drag, it's only lift, then lift is the same as resultant force. Now you can put this resultant force or lift anywhere along the chord. It's the same resultant force. So this is the quarter chord. So this is a C over 4 and this is the leading edge. The thing is, you can put the resultant force, the same resultant force at the same angle anywhere along the chord, but only at one place it will not have a moment along with it. For every other place you have to put the moment to get this correct static equivalence. So here you'll have something called M leading edge, and here you'll have something called M quarter chord, and at this place it just so happens that M equals 0. This is some arbitrary location on the airfoil. I'm not saying it's like at some specified location. So this distance is called XCP. So the moments here are positive as shown. In other words, I'm drawing the positive sign convention. In reality, that will be a negative value because the actual moment about the leading edge is going to be nose down for this kind of pressure distribution. So these three are actually statically equivalent because we put an appropriate moment about these things. It's like taking this pen and lifting it up I can lift it up with some moment about the back. I can lift it up with some opposite moment from if I lift it up from the front. But if I lift it up from center of gravity, I don't have to put a moment, right? It's the same thing. They're all, in all cases, the pin is level. And so in all cases, it's statically equivalent to this. Just a quick note about why this is the positive sign convention. That comes from aircraft. So in aircraft stability and control, SNC, stability and control, so the positive body axis goes like this, XB, and the positive y-axis goes this way, and the positive z-axis goes towards the floor. So positive M is about the y-axis. So nose up moment for this reason is a positive, that determines the positive direction. And so to take it to the airfoil level, you keep the same sign convention. Okay, so as we are going to see, later in thin airfoil theory, that CMC over 4 does not change with alpha. In other words, the aerodynamic center is at the quarter chord. This is for subsonic airfoils, the kind that we will be talking about in this course. So we can now connect the X location of the center of pressure with the Cm about the C over 4. So the XCP, or the X location of the center of pressure, and the value of C over 4, value of Cm C over 4. So to do that, we'll take all this equivalence diagram that we drew from 2 pages back. Okay, so we're going to connect these 2 pictures. In this picture, we have the resultant force at the quarter chord along with the moment about the quarter chord. In this picture, we have a resultant force at the XCP with no moment, right? But these 2 are statically equivalent. So we can write, and we can also write it about the leading edge too. So we started off with M leading edge, right, which is just this. So if we take the moment about the leading edge for this picture, the resultant force does not create a moment about this point, right, in this picture. So we get only M leading edge. Then we take, in all cases, let's take the moment about the leading edge. They should all be the same, right? So here we have MLE. Here we have MLE plus this force into this moment arm plus this moment arm, right? Sorry, I didn't say that correctly. So in this picture, the moment about the leading edge is this force times this moment arm and plus this moment in appropriate signs. I'm just giving the contributions. If you take the moment here about the leading edge, again you have contribution due to force times distance, and then the moment here is 0. So we're going to put all those together. So we'll say MLE, the first picture. The second picture, it is MC over 4 minus Y times C over 4. And that's equal to, the third picture is minus Y times XCP. So for most conditions, when we'll have small angles, again small angle means angle is small in radians. So even 10, 12, 15 degrees is usually, it satisfies this. So small angle and lift much greater than drag, which is how it is in most normal situations. Lift is approximately equal to Y. We saw this earlier. So therefore you can write MLE equals MC over 4 minus L times C over 4, and that's equal to minus L times XCP. So let's focus on this part. We get MC over 4 now is minus L times XCP minus C over 4. We can now divide both sides to write it in non-dimensional form. C squared dz, sorry. What a mess. So we get MC over 4 So this becomes pitching moment about the quarter chord, and this portion of this right hand side becomes lift coefficient. And so what we get is this pretty important equation which connects CMC over 4 and lift coefficient with center of pressure location. Sorry. Okay, so this is, we made a few assumptions along the way. So this is within the assumptions of thin airfoil theory, and which means thin airfoils and small angles and thin boundary layers, thin attached boundary layers. Which actually works most of the time all the way to stall, up to stall, as long as you don't have a very thick airfoil and big separated flow and that kind of stuff. So Um, let's put some numbers for a sort of typical airfoil and see what we are going to get. So I'm going to ask you to take a minute to work on this. So let's take an example airfoil. Assume an airfoil has a pitching moment coefficient about the quarter chord of minus 0.1. And if you look at experimental data for some typical airfoils, this is very reasonable. So at what condition is this pitching moment going to happen? Will it be at low lift coefficient, high lift coefficient, moderate lift coefficient? Or doesn't matter? And let's say lift coefficient is 0.1. How will pitching moment coefficient about the quarter chord vary with lift coefficient? Well, it won't change, right? Aerodynamic center for airfoil, subsonic airfoils, we are only talking about subsonic flow and all that, is at the quarter chord. So if pitching moment coefficient is minus 0.1 for some angle of attack, for some other angle of attack also, it will still be minus 0.1. It will be very close, as long as you don't go to stall and all that sort of stuff. So this is pitching moment coefficient about the aerodynamic center, so it doesn't change. So anyway, pull out your calculators and pencils and all that and tell me what is the value of xCp over C for this condition. It's like a quick 30-second calculation. So this is some kind of a pressure distribution. It all comes from some sort of pressure distribution, right? So maybe some pressure distribution is like this. What are you getting? Minus 3 by 4 xCp over C, right? Minus 3 over 4. What are you getting? Minus 1 plus 1.25 minus. And that's 5 by 4. You said 5 by 4. That's the same as this, right? Why are you getting minus 3.4, 3 over 4? I'm basically asking you to use this equation. What else are you getting?
We missed the minus sign initially.
This one?
Yeah.
Okay.
That's why we got minus 3 over 4.
Okay. So everybody agreeing on this? Okay, so what does this mean? Let's plot it. 5 over 4 xCp over 4 or xCp over C. So this is 0, this is 1, center of pressure is here. So, in the previous plots, look at how we drew this. You can put a resultant force here with some moment or here with some moment, or you can put it here and you're saying all this pressure is causing a resultant force that will act somewhere. Now we are saying it acts outside the airfoil. Maybe you have seen this in some other class. I think I talk about this in every course. Have we talked about this in wing theory or something? Okay, then you can't talk about, you can't tell me the answer. I'll ask you later, you guys. Maybe you remember, maybe you're thinking about it and wondering, yeah, we saw it somewhere else, what happened? So does this make sense? It's like saying, I've been talking about this, lifting this object from center of gravity and you can lift it without a moment, right? Now we are saying, here's the object and you have to lift it, but you have to lift it from here somehow and magically keep this pin horizontal. What's going on? How can a center of pressure fall outside the body? Okay, so please think about it, and we can talk more about it on Thursday. But I'd like you to bring it up. I might forget and just march on. So please do think about it. It's actually a very interesting question. I pondered about these things a lot and then said, that's what it means. And then like 1 year later, I came across it again. This was all in grad school. It was not in a course or something. Probably encountered it again and said, wow, how's that happening? And then I figured it out and then realized I had figured it out 1 year earlier and forgotten about it. And then over time, it's now hopefully gelled somewhat. Okay, so center of pressure, even from this equation, you can see that CMC over 4 is a constant, right? Because it's the aerodynamic center. C over 4 is the aerodynamic center. So when you change, so this is a constant. So when you change lift coefficient, which will happen when you change the angle of attack, this also will change. That means center of pressure will change. So if you take an airfoil, at some angle of attack, center of pressure will be in one location. At some other angle of attack, it will be in some other location. It moves around. And that's why it's inconvenient to use. There are some instances in which you need center of pressure, but most of the time it's more convenient to use CMC over 4. So CMC over 4, which can also be written as CMAC, because AC is practically at the quarter chord. So this does not change with CL or alpha. So AC here is aerodynamic center, and that's equal to C over 4 this comes from thin airfoil theory, as we just mentioned earlier. Okay. So the equivalents for a full airplane, full airplane basically means not just an airfoil but a wing with fuselage, tails and everything. So for an airplane, the aerodynamic center is the neutral point, and for in this so for the airplane, the pitching moment coefficient about the neutral point does not change with CL. Lift coefficient for an airplane is written as C capital L. Okay, so equivalent for aerodynamic center is the neutral point. What is the equivalent for center of pressure for an airplane? Where is the center of pressure for an airplane? We're just considering normal flight. Let's say an airplane in cruise flight, kind of flying horizontally in very stable, steady flight. Where is the center of pressure for the full airplane? Anybody from undergrad aerospace or other courses remember?
Would it be the CG?
Yeah, so it'll be at the CG. So CG of the airplane is where the entire mass can be put as a single weight force, right? Like that. Lift, all the lift distribution on the airplane, wings, tails, everything. If you put all that as a single lift vector, you put the lift and coincide it with the weight, assuming we are not having some engine that's causing pitching moment or something. So normal, just regular kind of airplane with no unusual thrust position or something like that. So lift and weight will have to coincide, right? If lift is behind the weight, it will cause a nose down moment, which means the airplane will not be in stable equilibrium flight. If the lift is in front, it will cause a nose up moment. So equivalent of center of pressure This is also called center of lift. So some people refer to center of pressure as center of lift. And so this is the point at which so we can put the entire lift with no accompanying pitching moment. That's always the defining thing about center of pressure or center of lift or center of gravity. So let's put that in a graphical format to kind of think through that. So if you have an airplane, and let's say here's the wing, and let's say CG is here. So that's where the weight acts. If you put the lift here, and this airplane is in trim, so you usually take moments about the CG. So if mCG equals 0, then the airplane is in trim. These are all different ways of saying the same thing. Is in longitudinal trim or equilibrium. But this condition will not result in pitch trim. Because the center of lift is here. We have not drawn an accompanying pitching moment, right? So we're just putting the entire lift here and the weight is here. So you can see that the airplane will start going nose down. If the pilot wanted to fly in this condition, if there's a nose down pitching moment, you pull back on the stick and cause a download on the tail with the elevators, right? So here you'll have the elevator, and you pull down, you'll cause a download. That will essentially move the lift forward until so here's the CG again. So the pilot will adjust the elevator until the lift coincides, the center of lift coincides with the center of gravity. And in this condition, the pitching moment about the CG will become 0. And so the airplane is in equilibrium. Again, so we are assuming that the thrust does not cause a moment. If the thrust, for example, if the engine is located somewhere, not too high or not too low, the thrust will not cause a pitching moment. Okay, so this is kind of where we wrap up the discussion of center of pressure and aerodynamic center. I do want you to think about how the center of pressure can end up outside the airfoil. What we are going to do now is start talking about how CP distributions change with different conditions or for different kinds of airfoils. And so the first thing that we're going to talk about is how does velocity or CP distribution change for a given airfoil with angle of attack. So we saw this earlier, right? Velocity and CP distributions look very similar as long as you plot the CP upside down with negative going up. Generally the shapes are somewhat similar. The exact shape will be different, but the trends will all be very similar. So we can talk about velocity distribution and how that changes with angle of attack, and that same trend carries over to CP distribution too. So we'll talk about V over V infinity, because as we move on to airfoil design, this is the plot we'll look at. It's kind of very similar to CP, so it's all fine. So, and then let's draw the airfoil below. So this is x over c of 1 to 0, and then velocity goes from 0 positive up. So let's say we plot the 0 angle of attack distribution, and I'll plot that in red. Something like this. Okay, so this is alpha 0. And usually the trailing edge point is just a little less than 1. So this is usually like 0.95 or something like that. Okay, so now let's draw it for, okay, first of all, what can you say about this airfoil? At 0 angle of attack, what is it doing? We just talked about being able to read CP distributions, right? You can say something but just by looking at a CP distribution. What is it? What can you say about it? It's producing lift. First thing you can say is, oh, there's an area between the upper surface and lower surface curves, so it's producing lift. Okay, well, I think that's a good start. So let's leave it there and go to some other angle. We'll go to 4 degrees. I'll draw that in black. This is just a sketch, so things are not going to be like super accurate. Well, should go like this. So this is alpha 4. And then let's draw alpha of 8. This is alpha of 8. And by the way, these things, these are all upper surface distributions, and these are, and these are lower surface distributions. Okay, so the top 3 are upper surface, the bottom 3 are lower surface. So again, I didn't draw this very accurately, but if you draw this like with some computer program or with actual CP distribution, like if you look at X-foil, when you run X-foil later, you'll run it for different angles of attack, you'll see how CP distributions change. This is the quarter chord or aerodynamic center. So first of all, what can you now say about CP distributions for these 3 angles of attack? From the CP distributions, what can you say? Very like first thing that hits you. Say it, just shout it out. What is that? Lift increases with alpha, okay? And we know this, right? If you take an airfoil and change angle of attack, lift will increase. You know this from, I mean, even if you did not do an aerodynamics course, you've heard it and you've seen it. So you can see that corresponds to the area. The area keeps increasing with increasing angle of attack. I heard all that noise in the hallway and I kept wondering if I'm going beyond time. So anyway, I have 2 minutes, right? Yeah. Okay. So you can see CL increases with alpha. What can you say about pitching moment? About the quarter chord? So in fact, this will become even clearer if you draw, for example, the 12-degree angle of attack. And I'll draw that with a dashed red line. you'll actually see much better plots than what I'm sketching here from the homework 1. When you do homework 1 like part B, you will actually, one of the problems is basically this. So this is alpha of 12 degrees. So pitching moment about quarter chord we know does not change with angle of attack. If pitching moment should not change with angle of attack, then these distributions should all have the same moment about angle of attack, even though the lift is increasing, right? That means the lift, you can see that this distance is 3/4 chord. It's this distance is more than this distance. This is quarter and this is 3/4. But yet your increase in lift should be such that moment does not change about the quarter chord. That means you should have more increase here because it's a smaller moment arm and less increase here so that they balance out. Less increase times more distance should be equal to more increase times less distance. So that's the reason you'll see these curves will diverge from each other. As you increase angle of attack, they'll increase much more quickly with angle of attack here than here. At the trailing edge, they'll all come together. So even when angle of attack increases, they'll all be close. At the leading edge, they'll be more far apart. Okay, so let me just finish that one thought and then we'll continue later. So velocity changes with angle of attack are greater at the leading edge region than over the aft portion of the airfoil. So this is consistent with CMC over 4 being invariant with alpha. Okay, so we'll continue this on Thursday and do think about that question we had in this class. Thanks.